pleasure to listen the session from this Enormance and Empowerment Women. I welcome you, ma'am.
Thank you, ma'am. Thank you for the such a wonderful introduction. First of all, I would like to thank the organizing committee. Uh, they are giving the wonderful platform for those preparing the TNSET. This is a great platform as well as a great step for those preparing TNSET. Um, so I am very happy to be a part of this society. So my topic in the set uh, syllabus is partial differential equations. So we are all very well know about that partial differential equation is one of the vast difficult area in mathematics. So we have to concentrate more on this subject. Uh, uh, Basically, for net and set, we have to concentrate the important subjects like algebra, real analysis, complex analysis, topology, differential equation, ordinary differential equation as well as partial differential equations, numerical methods, and statistics. So each topic has its own importance. So here I'm going to give a uh, uh, talk on partial differential equations. So first, the syllabus uh, for TNSET is limited only. The question is also uh, easy when we compare to CSER net. So if we prepared continuously,
Excuse me, ma'am.
yes ma'am,
Ma'am, sorry to interrupt you, ma'am.
yes ma'am,
Ma'am, is there any presentation, ma'am? Because the screen was not visible.
yes ma'am, I'm going to present my screen.
Okay, ma'am.
Okay ma'am. So TNSET question is very easy only. So if we continuously preparing for this TNSET exam, we can easily uh, uh, pass this TNSET. When we compare to CSE and NET, TNSET is easily clear to everyone. So partial differential equation, the syllabus is the syllabus is I'm sharing my screen. So the syllabus is first order and higher order PDE, and the solution procedures for that first order and higher order PDEs, and different types of method for solving the partial differential equations. So first, for solving the first order PDE, those partial differential equations can be classified into two types, that is linear and non-linear. For linear partial differential equations, we can use Lagrange's. Similarly, for nonlinear partial differential equations, we can use Lagrange's as well as Charpit methods, and the classification of partial differential equation. When we uh, uh, entering into higher order PDEs, then the classification of partial differential equations is coming into the picture. Classification means in that topic we are going to discuss the characteristic equation also. After that, the Cauchy's problem for first order partial differential equations, and then the solutions for higher order PDEs and the complicated PDEs, wave equation, heat equation, and Laplace equations. So these are the syllabus. We are going to discuss these topics one by one in our upcoming classes. So in the partial differential equations, here uh, uh, we are all very well known about the difference between the ordinary differential equations and the partial differential equations. I am going to briefly discuss that. Ordinary differential equations means the dependent variable is depending only on a single independent variables, say x. So here z is a function of z of x, so x is the only independent variable. Then we can say that ordinary differential equations. But partial differential equation means here z is a dependent variable. This dependent variable is depending on two independent variables, say x and y. So this function is changing with respect to these two independent variables. Therefore, the derivatives involving with respect to x and y is called the partial derivatives. So here two independent variables are x and y. So the derivatives with respect to x dou z by dou x, we can simply denote it as p. Similarly, the derivative with respect to y, we can simply denote it as q. This is first order derivatives, and for the second order derivatives, we can define like this. The differentiation with respect to x, dou square z by dou x squared, can be denoted as r, and the mixed derivative with respect to x and y is denoted as s, and the derivative with respect to y is denoted as t. These are the notation. If we know about this, already we have discussed why we are know what is the difference between ordinary differential equation and a partial differential equation. If z is a function of only one independent variable, then it is called ordinary differential equation. But if the differential equations involving two independent variables are more than one independent variable, then it is called a partial differential equation. These are the notations for the derivatives. For simplicity, we can use these notations. And these are the examples for the partial differential equations. So here dou z by dou x equal to a. If we use the notations, then we can write p equal to a. Because already we are using this notation for the derivative with respect to x. So p equal to a, we can easily write this partial differential equation. Okay, these are the examples for the partial differential equations. So here equation 1 and 2 are linear partial differential equation, but equation 3 is non-linear partial differential equation, because here the term dou z by dou y has the degree 2. So if the right handed side can be written as dou z by dou y into dou z by dou y. So the derivative is in a product. So this equation is a non-linear partial differential equation. So this is the concept. So linear partial differential equation means the dependent variable and its partial derivatives occur only in the first degree. Okay. So here this is an example. These are the examples for linear partial differential equation. Suppose the partial differential equation is not linear, then we can say that it is a non-linear. So non-linear means that the derivative is in product. Moreover, the independent variable. So here x is a independent. Sorry, not a, if independent variables means that there is no problem. Dependent variable and so for example, instead of here x, if it is z dou z by dou x means this is a dependent variable and its a derivative, they are coming in product. So this is non-linear partial differential equations. But this partial differential equation, uh, if we have x here, then it is also non-linear partial differential equations, since here the derivative is in product. That's why it is called a non-linear partial differential equation. Okay. So now we are going to discuss the solution of partial differential equations. There are three types of solutions. The first one is complete solution. Second one is a singular solution. Third one is a general solution. The fourth one is that is the particular solution. But these we will discuss about these three. The first one is complete solution means I am going to explain here very in a simple manner. So you just concentrate this concept alone. That is, already we have discussed here this dependent variable z is depending on x and y. So here I am considering only two independent variables. So if it is a complete solution means, if it is a complete solution means the number of independent variables should be equal to the number of arbitrary constants. So if here we are considering x and y are two independent variables. So if a and b are two arbitrary constants means if the solution has only two arbitrary constants, then we can say that that is the complete solution. This is the concept. You just concentrate this thing alone. So if the number of independent variables is equal to the number of arbitrary constants, then we can say that that solution is a complete solution. So here, if it is a differential equation, the general form is f of x, y, z, p, q. So f is a function of x, y, z, p and q. Then the solution is, so here there is no change in the variable x, y, z. So x, y independent variable is a dependent variable. But the derivative p, q is changed to, p, q are changed to a and b. So this is the complete solution. Singular solution means we have to eliminate these arbitrary constants. So if we can eliminate those arbitrary constants, so the if an equation has these five variables, then we can say that that is a complete solution. In the complete solution, if we can eliminate the arbitrary constants a and b, then we can get the singular solutions. So in the singular solutions, only three variables are present. They are x, y and z. So if a solution which contains only these three variables, then we can say that the solution is singular solution. The next one is general solution. In the complete solution, there are two arbitrary constants. Instead of one arbitrary constant, if we replace that one arbitrary constant into the function of another arbitrary constant. For example, we are going to replace the arbitrary constant b as the function of pi of a in the complete solution. Then we get x, y, z, a. Instead of b, we have pi of a. So here now we can see that there are only one arbitrary constant, but the one arbitrary constant is only a is there, and the another arbitrary constant is changed into arbitrary function. So if the solution has at least one of the arbitrary function, then that is called the general solution. So after that we have to differentiate with respect to A. Then we can, if we eliminate a single arbitrary constant in that solution, we can get the general solution. So here uh, uh, here just to concentrate these points also. So this solution involves two arbitrary constants, therefore it belongs to double infinite system of family of surfaces or single infinite system of family of surfaces. But the singular solution, this singular solution represents the envelope of two parameter family of surfaces. But the general solution is represents the envelope of one parameter family of surfaces. But singular solution, the envelope of a two parameter family of surfaces, but the general solution represents the envelope of one parameter family of surfaces. But in contrast, the complete solution involves infinite system of family of surfaces. Okay, either double or single. These three are the important solutions. Next. So already I have mentioned for the linear partial differential equation, the one of the famous methods is Lagrange's method. So for solving the first order linear partial differential equations, the Lagrange's equations is very important. This equation is of the form P small p plus Q small q equal to R. So already I have mentioned small p represents the derivative with respect to x. So dou z by dou x. Similarly, small q equal to the derivative with respect to y. So this is a linear partial differential equation. Here there is no non-linear term, and capital P, Q and R are the functions of x, y, z. For example, if we consider a partial differential equation xyp plus yzq equal to zx is a Lagrange's linear partial differential equation, since here it is of the form p small p q small q equal to r. So if it is in this form, then we can say that it is a Lagrange's equation. So first we have to write the auxiliary equation. So the auxiliary equation is dx by capital P equal to dy by capital Q equal to dz by r. So we have to solve this auxiliary equation, and we have to get two independent solution. If we get two independent solution, then we can write the general solution as pi of the first solution, that is u, comma the second solution, that is v, equal to 0. This is the format of the format of the solution of Lagrange's linear equation. Either we can write pi of u comma v equal to 0, or u equal to f of v, or v equal to f of u. That is the first solution u equal to the function of the second solution, or the second solution equal to the function of the first solution. So the solution of the Lagrange's linear equation, we can use any one of these three format. So let us consider one problem for better understanding of this type of solution, y square p minus xyq equal to x into z minus 2y. So first we have to identify which type of partial differential equation is this one. So here we can easily uh, find out this is Lagrange's, because this is capital P into P, capital Q into Q, and this is capital R. So the capital R should be in the right handed side. So we have to concentrate on that one. In some problem they have given in the left handed side itself to confuse us. So we have to clearly concentrate on that part. So the capital R should be on the right handed side. So here uh, P is y square, Q is minus xy, and R is x into z minus 2y. So the auxiliary equation is dx by y square, dy by x minus xy, dz by x into z minus y. So for solving these auxiliary equations, we have to choose suitable Lagrangian multipliers. That Lagrangian multipliers, so here, that Lagrangian multiplier should satisfy the condition LP plus MQ plus NR equal to 0. So we have to choose three Lagrangian multipliers, that may be any, but that should satisfy the condition LP plus MQ plus NR equal to 0. So like that we have to choose LMN in LDX plus MDY plus NDZ by LP plus MQ plus NR. So the chosen of LMN is very important for solving Lagrange's linear equation. So in the first problem, uh, uh, either we can use grouping method. If we choose any two ratios and simply integrating, we can get the solution. If the problem is simply, then we can easily find out the solution in that integration method. Otherwise we have to choose the Lagrangian multipliers. So here in the for finding the first solution, I am using the simple integration. So for that I am taking the first two ratios, dx by y square equal to dy by minus x. So y get cancelled. So dx by y equal to dy by minus x. So cross multiplying these ratios, then x dx equal to minus y dy. Then we can easily integrate. So x square by 2 equal to minus y square by 2, and the integrating constant is c1 by 2. So here integrating constant is C1 by 2. Here there is no restriction for choosing this integrating constant like C1 by 2. We can choose it as C1 also. So there is no problem in it. So here I am choosing C1 by 2. So you can choose any constant as a integrating constant. So if I multiply by 2 on both sides, then we get x square plus y square equal to C1. For finding the second solution, so this is the first solution. So here x square plus y square equal to C1. Let us consider this equation is the first solution, that is u of x comma y. Now I am going to find out the second solution v. So for that I am considering the last two ratios in this auxiliary equation, that is dy by minus xy equal to dz by x into z minus 2y. So here x get cancelled. So remaining term is dy by minus y equal to dz by z minus 2y. Cross multiply these two terms. So we get minus into z minus 2y into dy and y into dz. So if we cross multiply, then we get this equation. After simplification, we get 2y into dy equal to y dz plus z dy. So we are all very well known about this, the integration formula of this, that is uh, integration of uh, uh, integration of x dy plus y dx equal to xy, isn't it? So, so y dz plus z dy equal to yz. So left hand side 2y square by 2, so 2 2 get cancelled. So yz plus c2. So y square minus yz equal to c2. This is the second solution, b of x comma y. So the general solution can be written as pi of u comma v. That is, the first solution is x square plus y square. The second solution is y square minus yz. So pi of u comma v. This is the general solution. Otherwise, we can uh, um, write it as u equal to pi of v or v equal to pi of u. So x square plus y square equal to pi of y square minus yz. Otherwise, we can write it y square minus yz equal to pi of x square plus y square. So we can use any one of these three format for writing the solution. Okay, so more and also so there is no restriction for choosing the function pi. We can use any other function f, g or psi. We can use any other function. Okay, so this is the second type. So here we are going to choose the Lagrangian multipliers for finding the solution. So here this equation is of the form p plus q equal to r. So p is this one, and q is minus x plus z, r is x minus y. So the auxiliary equation is this one. So here already I have mentioned we have to choose the Lagrangian multiplier as any term, either it is a constant or variable, variable in the sense x, y, z, in terms of x, y, z. So here, uh, uh, if you choose the Lagrangian multiplier, the first one by first denominator, second one by the second denominator, and the third one by the third denominator. If you choose a 1 1 1 means, so you have to uh, uh, multiply the first denominator by plus 1. So here also plus 1, here also plus 1, and after that we have to add all those terms. So 1 into y plus z, that means 1 into y plus z means y plus z. 1 into minus x plus z, then that term becomes minus x minus z, plus 1 into x minus y, then that term becomes x minus y. So in the numerator also we have to do the same thing. So 1 1 1, so 1 into dx plus 1 into dy plus 1 into dz equal to any ratio. So any ratio means, because anyway the denominator is going to be 0, so if we cross multiply, then we get the right hand side is 0. So here we can write any one of the ratio here, or we can say any ratio. So dx plus dy plus dz, so the denominator becomes 0. So if we cross multiply, then we get 0. After integrating, we get the first solution, u of x comma y is x plus y plus z. So similarly, our aim is we have to uh, make the denominator as a 0 1 for choosing the suitable Lagrangian multiplier. So by practice, you can easily choose those Lagrangian multiplier. It is like a puzzle only. So you have to do some rough works. If you can easily choose the Lagrangian multiplier to make the denominator is 0. So here the first ratio is multiplied by x, the second ratio by y, and the third ratio by minus z. So x into uh, y plus z, y into minus x plus z, and minus z into x minus y. Uh, so x y plus x z minus x y minus y z minus x z plus minus into minus plus y z. So all the terms get cancelled in the denominator, so the denominator becomes 0. Then if we equate, if we cross multiply, then we get x dx plus y dy minus z dz equal to 0. After integrating, we get this one. So I am choosing the integrating constant is C2 by 2. So already I have mentioned you can choose any integrating constant, there is no issues in that. So the second solution B is x square plus y square minus z square. Therefore, the general solution pi of u comma v equal to 0. So pi of x plus y plus z comma x square plus y square minus z square equal to 0. So these are the condition for choosing the Lagrangian multipliers. So due to the time constraint, I am solving only 2 problems. If time permits, after completing all the topics, we will discuss previous year set question papers in the topic of Lagrangian linear partial differential equations. So I have planned for that also. The next one is Charpit method for nonlinear partial differential equation. So this Charpit method is also very important. Lagrange's in linear PDE, the Charpit method for nonlinear PDE is very important. The partial difference. Let us consider the partial differential equation f of x y z p q. So here dz can be written as dou z by dou x into dx by the definition of total derivative plus dou z by dou y into dy. So here dz by dou z by dou x is p, dou z by dou y is q. So dz equal to p dx plus q dy. So the auxiliary equation is very important in the Charpit method. So this equation itself will be asked in the question. So the for the Lagrange's linear partial differential equation, the auxiliary equation can be written in a simple manner. But for the Charpit method, the auxiliary equation is a little bit complicated one. That is, so here there are 5 variables. So we have to write down all those 5 variables: dx, dy, dez, dp, dq. Dx by minus fb, dy by minus fq. So already I have mentioned dz can be written as pdx plus q dy, isn't it? So this dz in the denominator dz p into dx isn't then minus p, just to multiply this by p. So minus p into fp p dx plus q dy. So p fp plus q fq. So multiply this by since dz equal to p dx plus q dy q dy. So dx means just this is for your understanding, but you can if you can easily memorize means then you can do like that. So p dx plus q dy equal to dz. So multiply this by p, this by q, and adding those two. So we get minus p into fp minus q into fq, and dp by fx plus p into fz. So here fz is common, but dp means multiply by p, dq means multiply by q, and p add with fx and dq add with fy. So this is the auxiliary equation for Charpit method. So now the question is find the complete solution of the equation z equal to px plus qy plus p square plus q square. So first we have to write this equation in f of x, y, z, p, q equal to 0 format. So we have to take this z as one side, that is the right handed side. So px plus qy plus p square plus q square minus z equal to 0. So this is f. Now we have to find out the derivative one by one. So we are in need of fp, fq, fx, fy and fz. So we have to find out the derivative of all the uh, variables. So first we can differentiate with respect to fp, that means dou f by dou p. So here the p term is there, here one p term is there. So p into x. So if you differentiate partially with respect to p means this p is 1. So 1 into x. So we get x. And if we differentiate p square we get 2p. So like that we can find out q. So this one is a q term, this one is a q term. So y plus 2q and fx. Fx means here this is the only term in x. So if we differentiate x then we get p alone. If we differentiate with respect to y means we get a q alone. So f is z. Here the only one term which involves is z. So if we differentiate with respect to z, we get minus 1. So we have to substitute these values into the Charpit equation. So dx by minus fp. So dx by minus fp means what is fp? X plus 2p. So we have to substitute dx by minus x plus 2p. So this is the first term, minus x plus 2p, and dy by minus fq. What is fq? Fq is y plus 2q. So dy by minus y plus 2q. And we know that dz is p into fp plus q into fq. So here minus sign is there, so multiply by minus sign also. So p into x plus 2q minus q into y plus 2q. And dp by fx plus p into fz. What is fx? P. So here p plus p into minus 1. So p and then p into minus 1. So what will we get? P minus p. Similarly, fy. What is fyq? Plus q into fz. So fz is minus 1. So q into minus 1 is minus q. So q minus q, isn't it? So dq by q minus q. So we get dp by 0. This term becomes 0. Similarly, this term becomes 0. So for finding the solution, considering the last two ratios, because all the remaining ratios are little bit complicated comparing the last two. So considering the last two ratios, then we get dp equal to 0. If we cross multiply these two ratios, then we get dp equal to 0 and dq equal to 0. After integrating, we get p equal to an integrating constant a and q equal to an integrating constant b. Substitute p equal to a and q equal to b in the given equation. What is the given equation? The question, that is z equal to px plus qy plus p square plus q square. Substitute p equal to a and q equal to b, then we get z equal to ax plus by plus a square plus b square. So here the question is we have to find out the complete solution. So complete solution means, by the definition what I have said, the complete solution means the number of arbitrary constants should be equal to the number of independent variables, isn't it? So here the number of independent variable in that problem is x and y, that is number of independent variables are x and y, that is 2. So here how many arbitrary constants are there in the solution? A and B. So there are two arbitrary constants, two independent variables. Therefore, this is the complete solution. Next, one more example, xp plus yq equal to pq. Okay, so this is a non-linear term. Okay, Are you able to understand why we can say that this is a nonlinear partial differential equation? Because the derivatives are in product, that is P is dou z by dou x into dou z by dou y. So we cannot solve this problem by using the Lagrange's. So we have to use the Charpit method or any other method, because the Lagrange's means only linear partial differential equations can be solved by Lagrange's. So here this is a non-linear term, so we have to use a Charpit method. So first we have to write f equal to 0. So xp plus yq minus pq equal to 0. So we know that this is the auxiliary equation for the Charpit method. Dx by minus fp equal to dy by minus fq equal to dz by minus p into fp minus q into fq, dp by fx plus p into fz equal to dq by fy plus q into fz. So first we have to find out the derivative one by one. The equation is xp plus yq, xp plus yq minus pq equal to 0. This is the equation, isn't it? So first we have to find out the derivative with respect to x. So the derivative with respect to x means, then we get here 1. So p is the only term. With respect to y means, so here y is this is the only one term. So if we differentiate with respect to y means 1 into q. Therefore 1 into q means q. Fz means here there is no term in z. So the derivative with respect to z means that term becomes 0. And fp. So fp means here there are two terms in p. So with respect to p means p is 1. So 1 into x, so x minus 1 into q, so x minus q. Similarly, with respect to q means yq minus pq. So if we differentiate, then we get y minus p. So we have to substitute all the those terms into the auxiliary equation. So we get like this equation. So just to go through, then you can easily understand just the substitution alone. So here also I am considering the last two ratios because they are the simple ratios. So dp by p equal to dq by q. So if we integrate, then we get dp by b means log p. If we integrate log q equal to log a, so p equal to aq. Next, we have to find out the another solution q also, because in the first problem we can easily get number of independent variable equal to number of independent variable. Therefore the complete solution exists. But here we are going to use this equation for finding the solution. D is equal to PDX plus QDY. So first for that we have to find out Q also. So here we get P equal to AQ. Substitute this relation into the given equation. So X into AQ plus YQ equal to AQ into Q, therefore AQ square. So we get Q uh, um, uh, in these two terms, take q as a common term. So we get ax plus y equal to aq square. Q get cancelled. So remaining term, in the remaining term we can easily find that q equal to ax plus y by a. So since p equal to qa, because p is in terms of q, so substitute the q value into this relation. So p becomes ax plus y by a into a. So a get cancelled. P equal to ax plus y. Substitute p value and this q value into this equation. So d is equal to ax plus y into dx plus ax plus y by a into dy, because this is the q value. After integrating here in the right handed side, considering taking a as a LCM, then we get a into ax plus y into dx plus ax plus y into dy equal to a into dz. In the right hand side, ax plus y is a common term. So we get ax plus y into adx plus dy. If we have x, just one, if we have x into dx means x into dx means after integrating this term, what will we get? X square by 2, isn't it? So instead of x, here we have ax plus y into a dx plus dy. So instead of x, here we have ax plus y. Instead of dx, we have a dx plus dy. Okay, so integral, consider this full term as x and this full term as dx. Then what is the formula for the integration? X square by 2. So instead of x, here we have ax plus y. So we can get the integrating value ax plus y the whole square by 2 plus the integrating constant b. Now have a look on this equation. So we get a and b are two constants. These two are arbitrary constants. So here the independent variables are 2. Therefore, the number of independent variables equal to number of arbitrary constants. Therefore, this is the complete solution. So next one is here the Charpit method is the general one. So the sub cases of the Charpit method are the simplified form of the Charpit methods can be classified into the following types. The first one is f of p comma q, and the second one is f of zpq xy. So this is an important form. This one is called Clairaut's form. So this is z equal to, so these three terms are fixed one. The last term will be vary for different problems, f of p comma q. So this is an important type, that is Clairaut's form. Type 3 is f of zpq. Type 4 is f of xp equal to g of yq. Because in the Charpit methods, all the 5 variables are exist, then the auxiliary equation have those derivatives involving all the variables. But in this subdivisions, if only two terms, they are p and q, then it is coming under type 1. Similarly, this is the second type. If the equation which has only 3 variables, they are zpq, then it is coming under type 3, and only 4 variables except z, then this is coming under type 4. So type 1, so we have to discuss the complete solution for these types, these 4 types. We will discuss these 4 types briefly. After explaining these 4, we will wind up this first session of partial differential equations. So type 1 is f of p comma q equal to 0. So the example for this type is root p plus root q equal to 1. So clearly we can see that there are only 2 variables are present. So only p and q. So only p and q means we have to assume the solution is z equal to ax plus by plus c. This is the standard form. So for this, we have to eliminate one arbitrary constant, because already we have discussed that the complete solution has only 2 arbitrary constants, because the solution, the equation has only 2 independent variables, they are x and y. So here in the assumed solution, there are three arbitrary constants. They are A, B, C. So we have to eliminate any one of these constant. So for this, we have to substitute P equal to A and Q equal to B in the given equation. If we identify this type, so then these two equations are common. So we have to substitute these two, then we get f of root a plus root b equal to 1, isn't it? Then we have to find out either a in terms of b or b in terms of a. That is your wish. So now I am going to write b in terms of a. So root b equal to 1 minus root a. After squaring, we get b equal to 1 minus root a the whole square. Substitute the b value in equation 1 in the assumed solution, then z equal to ax plus so here z equal to ax plus b. B means 1 minus root a the whole square into y plus c. Okay. So now in equation 3 there are only two arbitrary constants. They are a and c. Therefore, number of arbitrary constants equal to number of independent variables. They are x a equal a and c, which is equal to that means number the cardinality. So a c equal to xy. Therefore, this equation is called the complete solution for this problem. So similarly, we can solve all the problems in this type. We have to assume z equal to ax plus by plus c and p equal to a and q equal to b if this type of problem is asking in the examination. Next one is Clairaut's form. So Clairaut's form, the complete solution is very easy. So already I have mentioned these three terms are a fixed one. The last term only will vary. So here the last term in this problem is PQ. The first three terms are fixed one. So Z equal to Px plus Qy plus PQ. So substitute P equal to A and Q equal to B. This is the solution procedure for finding the complete solution of this Clairaut's form. Just replace P equal to A and Q equal to B, we get the complete solution. So what will we get? Z equal to Ax plus By plus AB. So here you can easily see that number of independent variables equal to number of arbitrary constants. Therefore, this is the complete solution. So third one is f of ZPQ. So the equation involving three variables, that is Z, P and Q. So for this we have to assume u equal to x plus ay and p equal to, after substituting this values in this derivative, we get p equal to dz by du and q equal to a into dz by du. That is, the partial derivatives can be transformed into the ordinary derivatives. Okay, for finding the solution, the partial differential derivatives dou z by dou y and dou z by dou x are transformed into the ordinary derivative dz by du and q equal to a into dz by du. Okay, so after substituting this, we can easily integrate, then we get the solution z. Okay, so here this is the example. So it's a square into p square plus q square plus 1 equal to 1. So here you can easily you can identify this is type 3 because only three variables z, p, q are there. So u equal to x plus y, ay, p equal to dz by du, q equal to a into dz by du. For type 3, we have to use this relation. So z square, instead of p, replace dz by du. So p square the whole, therefore here dz by du the whole square. Instead of q, we have to replace a into dz by du. So square this term plus 1 equal to 1. So after simplifying this, we get dz by du equal to this term. By variable separable method, separate z terms in the left handed side and u term in the right handed side. After integrating, we get root of minus root of 1 minus z square equal to x plus ay by root of 1 plus a square plus c. So after simplification, we get this thing. So here the arbitrary constant is a and c, independent variable x and y. Therefore, this is the complete solution. Next, type 4, f of xp equal to g of yq. In this type, there are 4 variables are involved. They are x, y, p, q. Except z, these 4 variables are present in this type. So, let us consider this example. In this example, PQ in one side, X and Y in on the another side. First, we have to separate P and X in one side, Q and Y in the another side. After that, we have to equate these two in a constant. Here, the solution is d is equal to P dx plus Q dy. So, in this example, p square minus q square equal to x minus y. So, first we have to separate p and x in one side, q and y in the another side. So, after separating, we have to equate that equation into a constant a. So, p square minus x is equal to a. Similarly, q square minus y equal to a, and find out the value of p and q for substituting into this equation. So, we get p equal to root of a plus x, q equal to root of a plus y. So, we get d is equal to root of a plus x into dx plus root of a plus y into dy. So, after integrating, dz becomes z. So, a plus x whole power 1 by 2. So, by using the integrating formula, x power n into dx equal to x power n plus 1 by n plus 1. So, by using this formula, here n is uh, 1 by 2, 1 by 2. So, 1 by 2 plus 1 is 3 by 2. So, a plus x whole power 3 by 2 by 3 by 2. Similarly, a plus y whole power 3 by 2 by 3 by 2. So, in the denominator, take the reciprocal and write it in the multiplication. So, 2 by 3, a plus x whole power 3 by 2 plus a plus y whole power 3 by 2 plus c. Okay. So, these are the 4 types. Okay. These are the 4 types. These are the subdivision of the Charpit method. So, we will wind up the class up to this. We will see the next topics in the next session. Thank you.
Ma'am,
Yes, ma'am.
ma'am, it was an amazing session, ma'am.
Ma'am,
It's really useful for us.
yes, ma'am. Thank you, ma'am. If is there any feedback?
Thank you so much for your valuable time, ma'am.
Yes, ma'am. Thank you. If is there any feedback about this class, please inform to me. Then it will be improved in the next coming classes. Thank you, ma'am.
Thank you so much, ma'am.
Thank you.